Welcome to the 7th lecture. In this lecture we shall review the fundamentals of heat and mass transfer. So, the specific objectives of this lesson are to present equations for basic modes of heat transfer, namely conduction, radiation and convection, introduce the concept of thermal resistance, discuss analogy between heat, mass and momentum transfers, and discuss multimode heat transfer, and finally introduce heat exchangers. So, at the end of this lesson you should be able to state basic laws of heat transfer, estimate heat transfer rates by different modes, use the concept of thermal resistance to solve steady state heat transfer problems, state and use the analogy between heat, mass and momentum transfers, and perform basic heat exchanger calculations. So, let us look at heat transfer. As we have seen in thermodynamics, heat transfer is defined as the energy in transit due to temperature difference, and heat transfer takes place whenever there is a temperature gradient within a system or whenever two systems at different temperatures are brought into thermal contact. Heat transfer cannot be measured directly, but the effects produced by it can be observed and measured. For example, when heat transfer takes place, some property of the system will change. For example, the temperature may change or some other property will change. So, by measuring the property or by observing the property, we can say that heat transfer has occurred. All heat transfer processes must obey the first and second laws of thermodynamics, because basically heat transfer is nothing but energy in transit. So, they have to obey the first and second laws of thermodynamics, but in addition to the first and second law of thermodynamics, we also have to apply certain rate laws of heat transfer to estimate the heat transfer rates. And estimating rate of heat transfer is a key requirement in the design and analysis of any refrigeration or air conditioning system. Now, let us look at the basic modes of heat transfer. As you know, probably the basic modes are conduction, radiation and convection. Even though we treat them separately, we find that in most of the engineering problems, heat transfer takes place by more than one mode simultaneously. That means you have what is known as a multi-mode heat transfer in most of the engineering problems. But when we are treating the subject, initially we treat them separately, and then we see how to club them when they are occurring simultaneously. Now, let us look at conduction heat transfer. Conduction heat transfer takes place whenever a temperature gradient exists in a stationary medium, and on a microscopic level, conduction heat transfer is due to the elastic impact of molecules in fluids, and in solids it is due to the molecular vibration and rotation about their lattice positions, and also due to the migration of free electrons. So, let us look at the Fourier's law of heat conduction. This is the basic law of heat conduction, and it is an empirical equation. So, that means it does not have any derivation, but it is based on the observations. So, this is the fundamental law of heat conduction. Okay. So, this law relates the heat transfer rate by conduction with the temperature gradient and area of cross section. As you can see that according to Fourier's law of heat conduction, heat transfer rate in x direction is equal to minus Ka dt by dx, where dt by dx is a temperature gradient in x direction, and A is the area normal to x direction, and K is a property of the medium, and it is called as thermal conductivity. And if you want to find out the heat transfer rate, obviously we need to know the temperature gradient. That means we should know the function of temperature, temperature as a function of spatial coordinates. Then you can find out the heat transfer rate by conduction, provided you know the thermal conductivity and also the heat transfer area. And the negative sign in this equation is a consequence of second law of thermodynamics. As you know very well, the second law of thermodynamics says that heat transfer takes place spontaneously from a system of high temperature to a system at low temperature. That means dt by dx will always be negative as decided by the second law of thermodynamics. So, if you want to make Qx as positive, you have to have this negative sign. So, the negative sign is a consequence of second law of thermodynamics. Now, let us look at typical thermal conductivity values. This table here shows typical thermal conductivity values for a large number of materials at 300 Kelvin. That means at a temperature of 27 degrees centigrade. So, from the table you can notice that all pure metals have very high thermal conductivity. Copper has a very high thermal conductivity of 399. Similarly, gold, aluminum, etc., they have very good thermal conductivity. That means they are all good conductors of heat. And compared to pure metals, alloys have lower thermal conductivity. For example, pure iron has a thermal conductivity of 80.2, whereas carbon steel has a thermal conductivity of only 43, and stainless steel has a thermal conductivity of 15.1. That means whenever you have alloys, the thermal conductivity will be lower. And compared to metals, non-metals have still lower thermal conductivity. For example, glass has a thermal conductivity of 0.81 and plastics have 0.2 to 0.3, and cork has a thermal conductivity of 0.039. Typically cork is a bad conductor of heat, so we use it as an insulating medium, not as a conducting medium. And another observation is that compared to the solids, liquids have much lower thermal conductivity, and compared to the liquids, gases have much lower thermal conductivity. And among the gases, certain gases like hydrogen and helium have reasonably high thermal conductivity values. Now I have mentioned that in order to find the heat transfer rate by conduction, you have to know the spatial variation of temperature. So to find the spatial variation of temperature, we have to solve what is known as the general heat conduction equation. So the general heat conduction equation is shown here for Cartesian coordinates with constant thermophysical properties. That means if I am assuming that thermophysical properties such as the thermal conductivity, specific heat, etc. are constant, and if I am applying first law of thermodynamics along with the Fourier's law of heat conduction to a Cartesian coordinate system, we arrive at this general heat conduction equation. In this equation, alpha, this alpha is your alpha is the thermal known as thermal diffusivity, and it is defined as K by rho Cp, and Qg is the heat generation per unit volume. So if you solve this general heat conduction equation, you get the solution gives you the temperature as a function of the three spatial coordinates x, y, z and the time tau. Of course, there are a wide variety of ways by which you can solve this particular equation, and you can derive similar equations by applying Fourier's law and first law of thermodynamics to other coordinate systems, for example in polar coordinates, etc. And in order to solve this, this is typically a partial differential equation, and if you want to solve this equation, you need to know certain initial and boundary conditions. So with the help of the initial and boundary conditions, you can solve this equation and get an expression for temperature in terms of x, y, z and tau. Now we can write this equation in a compact form using a Laplacian operator del square. For example, if I am using Laplacian operator del square, the general heat conduction equation for Cartesian coordinate system becomes 1 by alpha dou T by dou tau is equal to del square T plus Qg by K. And when there is no heat generation, obviously Qg by K term becomes 0, and you have a transient heat conduction equation without heat generation given by 1 by alpha dou T by dou tau is del square T. And when there is no variation with time, dou T by dou tau becomes 0, and you have what is known as a steady state heat conduction equation given by del square T is equal to 0. This equation is known as Laplace equation. Now let us apply this equation to a simple case of one dimensional steady state conduction. So for one dimensional steady state conduction, this is the basic equation, and to solve this equation we need to know two boundary conditions, and this is the typical geometry. We have, let us say, a wall, a thin wall whose dimensions in y and z directions are much larger compared to the dimensions in the x direction, and here we have two boundary conditions where x is 0, that means this thing we have temperature is equal to T1, and x is L, that means the thickness of the plate is L, at x is L the temperature is T2. So these are the two boundary conditions, and this is the governing equation d square T by dx square. So the solution is very simple. Solution is given by T at x at any x is equal to T1 plus T2 minus T1 into x by L. That means the temperature variation is typically linear, so you have a linear variation of temperature, and the heat transfer rate can be obtained by applying the Fourier's law here. Qx is minus Ka dt by dx. So temperature profile used from this equation, and then you get the expression for Qx in terms of the temperature difference delta T, where delta T is T1 minus T2, and the properties K and the thickness L and the cross section area A. So this equation can be written in this form, that means Qx can be written as delta T by R conduction, where delta T is the temperature potential which is driving the heat transfer, and R conduction is the conductive resistance. So, this equation is almost similar to analogous to Ohm's law. I mean, in Ohm's law for current we write I as E by R, where E is the potential difference and R is the resistance. So, this equation is also similar analogous to Ohm's law. Now, this conduction resistance obviously is given by R conduction is L by Ka. That means it is a function of the geometry of the system and also the property of the system, that is thermal conductivity. And you can also derive this one dimensional steady state heat conduction equation for a cylindrical wall. Let us say that you have a thin cylindrical wall, and if you apply energy balance, then you get the basic heat conduction equation, and if you solve the heat conduction equation by applying suitable boundary conditions, you arrive at the solution for temperature. This is the solution, and this solution, this temperature profile is logarithmic. In case of Cartesian coordinates, we had a linear profile, but this profile is logarithmic, and by differentiating this using the Fourier's law, you can get an expression for heat transfer rate in cylindrical coordinates. Again, you can write this as delta T by R cylindrical, where R cylindrical is the conductive resistance in cylindrical coordinates. In cylindrical coordinates, the conductive resistance, if you compare these equations, is given by ln R2 by R1 divided by 2 pi Lk. In this equation, R2 is the outer radius of the cylinder, R1 is the inner radius of the cylinder, K is the thermal conductivity, and L is the length of the cylinder. Now, let us briefly look at radiation heat transfer. As you know, radiation heat transfer does not require a medium for transmission. In fact, it is very efficient in vacuum. This is unlike the other modes of heat transfer which require a medium. And energy transfer in radiation occurs due to the propagation of electromagnetic waves, and all bodies having a finite temperature emit electromagnetic radiation, and this electromagnetic radiation propagates with the speed of light in straight line in a vacuum, and if you have a medium, its speed is reduced, but still it travels in a straight line in a homogeneous medium. And the basic law for radiation energy emitted by a surface is given by Stefan Boltzmann's law, and this law is derived by integrating Planck's equation. Okay. So, in this equation is simply given by QR is equal to epsilon sigma A Ts to the power of 4, where QR is the rate of thermal energy emission in watts, and epsilon is the emissivity of the surface, and sigma is Stefan Boltzmann's constant, its value is given here, and A is the surface area, and Ts is the surface temperature in absolute units. Unlike the conduction and convection equations, the Stefan Boltzmann's law can be derived from basic thermodynamics. That means it is a derived this thing, it is not only an observation, not only based on observation. And here the emissivity is a property of the surface, and if emissivity is 1, we have a surface which is ideal. That means for an ideal surface, the emissivity is 1, and such a surface is known as a black body. A black body has nothing to do with a black color. Black body is an ideal emitter. That means it emits at a given temperature, a black body emits the maximum amount of radiation. Similarly, it absorbs the maximum amount of radiation. So, such a body is called as black body, and all real bodies have emmissivities less than 1. So, all real bodies have emissivity less than 1, and emissivity, the definition of emissivity itself, it is defined as the emissive power of a real body divided by the emissive power of a black body at a fixed temperature. Okay. Now, let us look at the radiation heat exchange between any two surfaces 1 and 2, which are at two different temperatures T1 and T2. So, this is it can be shown that this is given by Q12 is equal to sigma into A into F epsilon into F A into T1 to the power of 4 minus T2 to the power of 4, where Q12 is the radiation heat transfer between surfaces 1 and 2, and F epsilon is what is known as the surface optical property factor, which depends upon the properties of the surfaces participating in radiation. So, basically it is a function of emissivities of the surfaces, and you also have a factor Fa, which is known as geometric shape factor or configuration factor, and T1 and T2 are obviously surface temperatures of 1 and 2 in degrees Kelvin, that means in absolute temperature scale. So, the major problem in radiation is the evaluation of the factors F epsilon and Fa. Normally we know the temperatures T1 and T2, and we also know the surface areas, etc. So we have to find out the factors F epsilon and Fa. So unlike the other modes of transfer, radiation transfer between two surfaces depends upon the orientation of the surfaces. So the factor, geometric factor or configuration factor, takes care of the orientation of the surfaces. For example, if the surfaces do not see each other, then there will not be any radiation exchange between them. Okay. Now we can also write the temperature radiation heat transfer in terms of temperature potential and resistance. Of course, if you look at the radiation heat exchange equation, we have temperature terms not in linear form but in a non-linear form. That means Q is proportional to T to the power of 4, but still you can linearize it, and you can write Q radiation as T1 minus T2 divided by R radiation, where R radiation is the radiative heat transfer resistance defined in the manner shown here. And you can see that radiative heat transfer resistance depends not only on the factors F epsilon and Fa, but it also depends upon the temperatures in a non-linear fashion. But it so happens that in most of the practical problems, when the temperature difference is moderate, then you can assume the radiative heat transfer coefficient to be linear. That means we can linearize the radiative heat transfer and write it as a function of temperature potential and a resistance. We shall see later what is the advantage of writing heat transfer rate in terms of a potential and a resistance. Now let us look at the other very important mode of heat transfer known as convective heat transfer. So convection heat transfer takes place between a surface and a moving fluid when they are at different temperatures. And convective heat transfer resistance consists of two mechanisms operating simultaneously. This is important. What are the two mechanisms? The first mechanism is the energy transfer due to conduction through a fluid layer adjacent to the surface. Now if you remember in the last lecture, I was mentioning hydrodynamic boundary layers. When a fluid flows over a surface, the fluid layer adjacent to the surface attains the velocity of the surface. If the surface is stationary, the fluid layer also becomes stationary. So this is what is known as a no slip condition, and the boundary layer is known as hydrodynamic boundary layer. Similar to hydrodynamic boundary layer, when a fluid flows over a surface whose temperature is different from the fluid surface, then the fluid layer adjacent to the surface attains the temperature of the surface. Again, this is because of your no slip condition. Okay, that means we have a stationary layer on the surface where the temperature is same as the surface temperature. That means similar to a hydrodynamic boundary layer, a thermal boundary layer also develops, and the temperature varies in this thermal boundary layer from the surface to that of the free stream. So you can see the similarities between the momentum transfer and convective heat transfer and hydrodynamic and thermal boundary layers. And the layer which, as I said, is stationary, the layer close to the plate is stationary. So the mode of heat transfer through the stationary layer has to be obviously conduction. Okay, so initially we have conduction heat transfer taking place from the surface to the fluid through a stationary layer by conduction. Then heat transfer heat transfer will be by the bulk motion of the fluid particles. So the second mechanism is energy transfer by macroscopic motion of fluid particles by virtue of an external force. So conduction is followed by macroscopic motion of fluid particles. And what is causing the macroscopic motion? An external force causes the macroscopic motion of fluid particles, and this external force could be generated because of the presence of a fan or pump. For example, a fan or pump is driving the fluid over the surface. Okay, then that causes the fluid flow and the mixing of the fluid particles. Such a type of convection is known as forced convection. That means whenever we are using an external source such as fan or pump, we call that convection as forced convection. It is also possible to have convective currents in the absence of any external device. This is known as a free convection. This free convection takes place because of the buoyancy effects. That means when a fluid comes in contact with a surface whose temperature is different from the fluid temperature, then there will be temperature gradient. And as you know, fluid density depends upon temperature. So when the temperature varies, density also varies. So due to the density variation, buoyancy effects are generated and fluid flow is generated. This is known as free convection. Now, the basic heat transfer rate by convection is written in a very convenient fashion as Q is equal to HCA into TW minus T infinity, where HC is the convective heat transfer coefficient, A is the area of heat transfer, TW is the surface temperature, and T infinity is the temperature of the fluid in the free stream. This equation, which is called as the basic equation for heat transfer by convection, is also known as Newton's law of cooling. And basically this is a definition of heat transfer coefficient. It is not actually a law, but it defines the heat transfer coefficient. And as I mentioned, since near the surface the heat transfer rate is by conduction, we can show that Hc is nothing but minus Kf dt by dy at y is equal to 0 divided by Tw minus T infinity. By writing the heat transfer rate in terms of conduction for the stationary layer and equating that to Newton's law of cooling, you can arrive at this expression. Now, the convective heat transfer coefficient from this equation obviously depends upon the thermal conductivity of the fluid, the temperature difference Tw minus T infinity, and the temperature gradient dt by dy at y is equal to 0. That means, what is the temperature gradient near the surface? Now, this temperature gradient near the surface dt by dy at y is equal to 0, y is the direction perpendicular to the surface, so keep it in mind. So, dt by dy at y is equal to 0 depends on the rate at which the fluid near the wall can transport energy into the main stream. So, it basically depends upon the fluid flow. That means, in convective heat transfer problems we have to consider fluid flow in addition to the heat transfer. That means, this mode of heat transfer is governed not only by the heat transfer laws, but also by the fluid flow laws. So, some people do not consider convection heat transfer as a basic mode, because here you have both heat transfer by conduction as well as fluid flow. Okay, but still for convenience sake we consider this also as one of the basic modes of heat transfer. Let me show typical convective heat transfer coefficients. This table shows the type of fluid and flow. Remember that once again I am repeating it, convective heat transfer coefficient depends on the type of the fluid and on the flow and also on the geometry. And if you have air in free convection, that means heat transfer is driven by density differences, then heat transfer coefficient varies between 6 to 30 watt per meter square Kelvin. And if you have water again in free convection, then you have heat transfer coefficient slightly higher, 20 to 100. So, you can see that water is gives much higher heat transfer coefficients compared to air. This is due to the higher thermal conductivity of liquid. Then if you have forced convection, then you have higher heat transfer coefficients. Forced convection, the fluid is air or superheated steam, then the heat transfer coefficient varies from 30 to 300. So, you have one order of magnitude higher than the free convection. This is because of the vigorous mixing of the fluid when you have forced convection. When you have oil in forced convection, again you have 60 to 1800. This is higher than the air because you are dealing with a liquid. And if you have a water, you get much higher heat transfer coefficient because water has typically a higher thermal conductivity compared to oils. And if you have phase changes such as boiling or condensation, you get really high heat transfer coefficient. For example, in case of synthetic refrigerants, under boiling condition you have heat transfer coefficient which vary anywhere between 500 to 3000 watt per meter square Kelvin. And if you have water, then you get really good heat transfer coefficients, again because water has excellent thermophysical properties compared to synthetic refrigerants. So, you can get heat transfer coefficient from 3000 to 60,000. And similarly in condensation, generally condensation gives much higher heat transfer coefficients compared to any other mode of heat transfer. So, you can see that you get very good heat transfer coefficients when fluids are condensing. Typically with steam you can get heat transfer coefficient as high as 1 lakh watt per meter square Kelvin. Now, similar to conductive and convective heat transfer, conductive and radiative heat transfers, you can also write the convective heat transfer rate in terms of the temperature potential and the resistance. So, you can write Q as Tw minus T infinity divided by R convection, where R convection is the heat transfer resistance to convection. And if you compare this equation, you can easily show that R convection is nothing but 1 by Hc into A. And the major problem in all convective heat transfer problems, the way it has developed, is the estimation of heat transfer coefficient. So, you can see that almost the entire literature on convective heat transfer coefficient is devoted to evaluation of heat transfer coefficient, because once you know the heat transfer coefficient, you can find out the heat transfer rate by multiplying that into temperature difference and surface area. Now, how do we evaluate the convective heat transfer coefficient? You can evaluate it analytically for simple cases. If you want to evaluate it analytically, you have to solve mass, momentum and energy equations. Since this can be pretty complicated, this method is possible only for simple situations. Simple situation means, let us say that laminar fluid flow is taking place over a flat plate. Then you can have analytical solutions and you can find analytical expressions for heat transfer coefficient. Similarly, laminar fluid flow is taking place over a cylinder. Again, you can have a closed form solution and an analytical solution. But when you have complicated cases, for example, when you have turbulent flow and when you have complicated geometries, then it is very difficult and you cannot have analytical solutions. And in such cases, what is done is you have to go either for numerical methods, or most popularly people use experimental methods in addition to the dimensional analysis to arrive at expressions for heat transfer coefficients. That is what is mentioned here. Most of the convection heat transfer data is obtained through careful experiments, and equations suggested are mostly empirical. Once you have empirical equations, they are valid for only a set of conditions under which these equations were derived, and they are also applicable to only that particular range of experiments. So, you must be very careful when you are using the empirical correlations. You must check that your problem falls in the range of that particular correlation, only then use it. And fortunately, because of the huge amount of work done in this area, you have correlations for almost all practical situations. So, you have to look for them in suitable heat transfer data books and textbooks. And to some extent, generalization has been made possible by introducing several non-dimensional numbers. Usually you will see that, probably you remember from your basic course on heat transfer, that several non-dimensional numbers such as Reynolds number, Nusselt number, Prandtl number are introduced, and generally the correlations are given in terms of the non-dimensional numbers. This will generalize the correlations to a large extent. I will show you one typical heat transfer correlations. This is known as the Dittus-Boelter equation, and this is valid for fully developed turbulent flow inside smooth tubes. So, this is valid for smooth tubes, and it relates a non-dimensional parameter Nusselt number, which is defined as the Hc d by Kf equal to 0.023 Re to the power of 0.8 and Pr to the power of 0.n. So, Nu is the Nusselt number, and it is equal to Hc d by Kf, where Hc is the convective heat transfer coefficient, d is a length parameter, and Kf is the thermal conductivity of the fluid. And on the right hand side, you have Reynolds number Re, and also you have another dimensionless number known as Prandtl number. Prandtl number is defined as, you can see here, Prandtl number Pr is Cp mu f by Kf. All the properties are that of the fluid, that is why the subscript f stands for fluid. So, Prandtl number is Cp mu by K, which can also be written in terms of kinematic viscosity nu divided by the thermal diffusivity alpha. So, Prandtl number is basically nu by alpha, and this Dittus-Boelter equation, there is another parameter n, and this n will take the value of 0.4 for heating. That means, when the fluid is getting heated, you have to use a value of 0.4 for n, and if the fluid is getting cool, then you must use a value of 0.3. This is a very popular empirical correlation, very widely used for, as I said, for fully developed turbulent flows inside the tubes. And if you are using a hydraulic diameter, you can also use this to non-circular tubes. But this is again valid for certain Reynolds number range, and this is also valid for certain Prandtl number range. So, when you are using this equation, you must know what is the range under which this can be used. This is just one example of a typical convective heat transfer correlations. A large number of correlations, as I mentioned already, are available for a wide variety of flow situations. That means, you have heat transfer correlations for forced convection, free convection over flat plates inside the tubes, and heat transfer correlations for phase change, boiling, condensation, etc. So, all these things have been derived and they are available. So, we will be discussing these things in detail when we are designing evaporators and condensers in later lectures. Now, let us quickly look at mass transfer. Mass transfer takes place when a system containing 2 or more components whose concentration vary from point to point, then there will be a natural tendency for mass to be transferred so that the concentration difference can be minimized. That means, when you have a system which consists of 2 or more constituents or components, and if there is a concentration difference, then the spontaneous process is to reduce the concentration gradient. That means, there will be mixing of the components. That means, there will be mass transfer. That means, transfer of one constituent into other. This is what is known as mass transfer. So, the mass transfer can be defined as the transport of one constituent from a region of higher concentration to that of a lower concentration is called as mass transfer. Why do we study mass transfer in refrigeration and air conditioning? Because we in refrigeration and air conditioning we typically encounter several cases where mass transfer takes place. A typical example of mass transfer which all of us are familiar with is that of drying. For example, when you leave a wet cloth in an unsaturated or dry air, then the cloth becomes dry. So, what has happened? Water vapor or water from the wet cloth is transferred from the cloth to the surrounding air. So, this is one popular case of mass transfer. So, we have this typical drying problem in air conditioning, because air conditioning latent heat is involved. So, we will be applying these principles when we are solving those problems. Another very familiar case of mass transfer is the spread of perfume. For example, when you put a perfume in one corner, because of the diffusion the perfume spreads all over the room. So, this is another example of mass transfer. Now, let us look at some very basic equations of mass transfer. The first basic equation is what is known as Fick's law of diffusion. This law deals with transfer of mass within a medium by molecular diffusion process, and it is given by m dot A is equal to minus dAb A dCA by dx, where dAb is known as a diffusion coefficient for component A through component B, and dCA by dx is the concentration gradient. So, you can see the similarity between Fick's law and Fourier's law for heat conduction. The similarity arises because both are diffusive processes. That is why the equations are similar. Again, you can see that just like Fourier's law of heat conduction, you also have a negative sign here. This means that mass transfer always takes place from a region of higher concentration to a region of lower concentration. And similar to convective heat transfer, we can also have convective mass transfer. This takes place whenever a moving fluid between a moving fluid and a surface, or between two relatively immiscible moving fluids. For example, you have, let us say, the two different fluids which come in contact with each other. Okay, then for example, you have a concentrated sugar solution and you slowly pour water over that. So, you have two different fluid layers, that slowly sugar spreads throughout the solution, and the entire solution reaches a uniform concentration. So, mass transfer takes place in this process. So, this is a typical example of convective mass transfer. And similar to Newton's law of cooling for convection, we can also write convective heat mass transfer as m dot is equal to Hm A into delta Ca, where Hm is the mass transfer coefficient, A is the mass transfer area, and delta Ca is the concentration difference. Now, let us look at the analogy between heat and momentum transfer. This is very interesting. We have seen that the mass transfer, momentum transfer, and heat transfer by convection all appear to be similar, because all of them have many peculiarities. For example, between momentum and heat transfer, you have a hydrodynamic boundary layer which takes care of the momentum transfer, and analogous to that you have a thermal boundary layer. Because of no slip condition, velocity becomes 0 on the surface, and similarly the fluid temperature becomes that of the surface temperature, again because of the no slip conditions. And mathematically, if you look at, for example, you take a case of laminar fluid flow over a flat plate. If you look at the momentum equation and the energy equation, you will find that they are exactly identical when Prandtl number is 1 and when there are no pressure gradients in the direction of flow, and when there is no viscous dissipation, and when there are no heat sources, then you will find that momentum and heat transfer equations are exactly identical, and if they have similar boundary condition, the solutions also will be identical. So that means there is a direct analogy between momentum and heat transfer. This is the observation, and for this condition it can be easily shown that a non-dimensional parameter Stanton number, which is given by Nu by Re into Pr, which is equal to Hc by rho Vcp, where V is the fluid velocity, is equal to F by 2. So this is known as Reynolds analogy. So what is the use of this Reynolds analogy? You can see that Reynolds analogy connects heat transfer coefficient Hc with friction factor F. That means if we know the friction factor, you can find out the heat transfer coefficient by applying this analogy. You do not have to carry out any heat transfer experiments. So this is very useful. This Reynolds analogy is strictly applicable for Prandtl number 1. So Colburn has improved this for different Prandtl numbers, and he has arrived at this what is known as Colburn analogy. This is given by Stanton number into Prandtl number to the power of 2 by 3 is equal to F by 2. This is known as Colburn analogy. This is applicable to a Prandtl number varying from about 0.6 to 50. So this is you can see the usefulness of this. Now let us look at analogy between mass and momentum transfer. Similar to heat and momentum transfer, we can also write analogy between momentum and mass transfer, and here we define another non-dimensional number called Sherwood number Sh, and this Sherwood number is defined as Hm into L by D, where Hm is the mass transfer coefficient and D is the diffusion coefficient and L is a length parameter. So Sherwood number is analogous to Nusselt number, and we also define another non-dimensional number called Smith number. This Smith number is analogous to Prandtl number. So when you are applying this analogy, you can show that mass transfer coefficient Hm divided by the velocity is equal to friction factor divided by 2. This is valid for Smith number equal to 1. So to take care of the Smith number other than 1, we can modify this similar to Colburn analogy, and we have the modified analogy given by Sherwood number divided by Reynolds number into Smith number to the power of 2 by 3 is equal to F by 2. This is the analogy between mass and momentum transfer. Now if you compare analogy between mass and heat, momentum and heat transfer, and momentum and mass transfer, you can arrive at this important expression. You can look at this. You can show that the heat transfer coefficient divided by the density into specific heat at constant pressure and Hm is equal to alpha by D to the power of 2 by 3. Okay, so this is from the comparison of the two analogies. This is a very useful expression, particularly for air conditioning calculations, because for air conditioning calculations, this parameter alpha by D to the power of 2 by 3 called as Lewis number Le, this takes a value of 1 for air water mixers, not exactly 1, but it is close to 1. So when this is close to 1, then your heat transfer coefficient is nothing but a product of density into specific heat into mass transfer coefficient. So if you know the heat transfer coefficient, directly you can find the mass transfer coefficient. So this is very useful, and we will be applying this when we do the air conditioning calculations. Now let us look at multi-mode heat transfer. So far we have been discussing and we have been describing the different modes of heat transfer separately. First we have given equations for conduction heat transfer, then convection heat transfer, then radiation heat transfer. That means we have delinked the different modes. But as I mentioned, in most of the engineering problems, the heat transfer takes place by more than one mode at the same time. That means you have what is known as a multi-mode heat transfer. So let us see how we look at how we solve the multi-mode heat transfer problems. As I said, in most of the practical heat transfer problems, heat transfer occurs due to more than one mechanism, and using the concept of thermal resistance which we have developed earlier, it is possible to analyze steady state multi-mode heat transfer problems in a simple manner similar to electrical networks. So remember that this concept of thermal resistance and networks is applicable only to steady state problems. If you have unsteady state problems, you cannot directly apply the concept of thermal resistance and networks. Okay. Now let me give an example of a building wall. Okay. Yeah, so you have yeah, stop recording for a moment, please. Okay, so let me show an example of multimode heat transfer applied to a building. So here we have two rooms, room 1 and room 2. They are at two different temperatures. For example, in this particular case, room 1 is at a higher temperature compared to room 2. So there will be heat transfer between room 1 to room 2, and the surroundings of the room 1 are also in this particular thing at the same temperature as that of the room temperature. That means the air and the surrounding surfaces are of room 1 are at temperature T1. Similarly, the room 2 has surface temperature at T2 and air temperature is also at T2. So you have two different temperatures, and these two rooms are separated by a multi-layered wall. Okay, so this wall is a multi-layered wall. That means it consists of three layers: layer 1, layer 2 and layer 3. Okay, and here the heat transfer is also by multi-mode. For example, look at here the heat transfer heat transfer takes place first by radiation from the surface surrounding surfaces to the wall, and also by convection from the air to the wall. So you have radiation heat transfer taking place and convection heat transfer taking place from surroundings and the air of room 1 to the wall. Okay, so the radiation and convection will be happening simultaneously. Okay, then from this point onwards the heat transfer to through this wall is by conduction. So you have initially radiation and convection, then conduction through the wall, and from the wall to the room 2, which is at lower temperature, again the heat transfer is by radiation and by convection. Okay, because you have radiative heat transfer here, because the surface temperature of the wall is different from the surface temperature of the surroundings of room 2. So you have radiation. Okay, similarly this air temperature T2 is different from this surface temperature, so again you have convection. Okay, so this is a very peculiar and typical example of multimode heat transfer, which we will be dealing with while doing air conditioning calculations. Okay, so this is look at the picture carefully. Now we can also draw the temperature profile. For example, if this is the temperature T1 of room 1, then let us assume that this temperature is uniform in the room, then there will be a temperature drop at this point because of the resistances, convective and radiative resistance. There will be a temperature drop here, and there will be a further temperature variation within the wall because of the conductive resistance. So the temperature profile varies like this. Again, from the wall to this room 2, you have again a temperature variation because of the convective and radiative resistances of this room. Okay, so this is a typical temperature variations of for this particular problem. Normally we know these two temperatures, and we also know the properties. For example, let us say that we know the properties of the walls 1, 2, 3, that means thermal conductivity, lengths, areas, etc. And we also know, for the time being, let us say that we know what is the heat transfer coefficient here, what is the heat transfer coefficient here, what is the radiative heat transfer here, and what is the radiative heat transfer here. So the basic objective here is to calculate the heat transfer rate from this room to the other room. So we can write a radiation network now. Okay, I hope you remember the physical model. We can write the radiation network. Initially we have the temperature T1 of room 1, then two modes of heat transfer taking place simultaneously. One is the radiation, the other one is convection. So you have radiative heat transfer and convective heat transfer. We write it in the form of parallel a network with parallel connection because they are happening simultaneously. So you have two resistances in parallel. One is radiative resistance, the other one is convective resistance. So this is the temperature of the surface of the wall inside the room. Okay, this is TS1, and from this point to this point the heat transfer is taking place through the wall. So, you have 3 different layers. This is the conductive resistance of layer 1, conductive resistance of layer 2, conductive resistance of layer 3. Okay, so, the mechanism is conduction and all the resistances are in series. So, you have a series resistances in series here. So, this is the temperature of the surface of the wall inside room 2. So, remember that at this point again the heat transfer takes place parallelly by radiation to the surrounding surfaces and by convection. So, again you have a parallel network here. So, this the whole thing is a typical heat transfer network for the problem discussed now. Okay. And this radiation network, as you remember from your basic electrical technology, this can be reduced to this form. So, what we have done here is this resistance, which is the resistance offered by the radiation and convection of room 2, can be clubbed together because they are in parallel. So, you can find out an equivalent resistance R2. As you know, parallel resistance means if the resistance is as R1 and R2, so you know that R parallel is equal to R1 into R2 by R1 plus R2. Okay. So, this is nothing but this. Okay. Here R1 and R2 refer to radiative resistance and convective resistance. So, what I have done is I have reduced this to an equivalent resistance R2. Similarly, this portion can be reduced to an equivalent resistance R1. So, we have now 3 resistances in series R1, Rw and R2. Rw is nothing but the equivalent resistance for the composite wall. Okay. So, this is the resistance simplified in the resistance network for the given problem. So, now what is the total resistance? As you know, the total resistance R total is nothing but sigma R. So, here it is simply equal to R1 plus R wall plus R2. Okay. So, we can find out what are the individual resistances, because we have already given the expressions for radiative resistance, convective resistance, conductive resistance, etc. And if you have the property data and other data, you can find out individual resistances and find the total resistance. And once you know the total resistance, you can find out the total heat transfer rate, because as you know, heat transfer rate is nothing but T1 minus T2 divided by the total resistance. Okay. So, you can see the usefulness of the network analogy. Okay. The complicated problems can be easily broken down into simple problems, right. And here we have shown the conductive resistances in series. It is also possible to have conductive resistances in parallel. A very typical case is heat transfer through a hollow brick. Okay. When you have a hollow brick, you find that inside the brick the heat transfer is in a parallel mode, because it is not homogeneous. Okay. So, this is the mathematical this thing whatever I have discussed just now. You can write for this multi-layered wall Q1 to 2, that means from room 1 to room 2 as T1 minus T2 divided by R total, where R total consists of these resistances. This is the equivalent resistance of the two parallel radiative and convective resistances in parallel for room 2, and this is for the room 1, and this is the resistances in series for the wall, and this is the total resistance, and this is the heat transfer rate. Now, you can also write the heat transfer rate in terms of what is known as overall heat transfer coefficient. So, you can write either like this, or you can also write Q1 to 2 as UA into T1 minus T2, where U is what is known as overall heat transfer coefficient. You probably might have heard of this when you are doing heat transfer calculations, and when I am comparing this equation with this equation, you find that overall heat transfer coefficient is nothing but 1 by R total into A. So, if you know the resistances, you can calculate the overall heat transfer coefficient. The concept of overall heat transfer coefficient will be used very widely when we are designing the heat exchangers. Okay. Now, let me give another example, that of a composite cylinder. This is also very commonly encountered. So, here what we have is a metallic tube. Okay. This is a metallic tube through which a fluid is flowing. Okay. And this is an insulated tube. So, outside you have insulation, right. So, an insulated tube through which a fluid is flowing, and let us say that the fluid temperature is different from the surrounding temperature. So, surroundings have a temperature of T0, whereas the fluid has a temperature of Ti. Okay. then there will be obviously heat transfer depending upon whether T naught is greater than Ti, as Ti is greater than T naught, there will be heat transfer from the fluid to the outside or from the outside to the surface, outside to the fluid, sorry. And what is the heat transfer rate? The heat transfer rate can be written like this: Q is equal to U naught A naught into Ti minus T naught, where Ti is the fluid temperature inside the tube and T naught is the outside surrounding temperature, and where A naught is the outside surface area of the tube. That means surface area referred to the outside surface. Okay, this is A naught. Okay, typically pi d naught into L, where d naught is the outside diameter. So I can write Q as UA into Ti minus T naught. And what is U? As you know, just now we have shown that U is nothing but 1 by R total into A. Okay. So what are the different resistances here? We have one resistance, that is convective heat transfer resistance inside the tube because of the fluid flow, and we have one resistance offered by the tube wall, and then we have another resistance offered by the insulation. Finally, we have another resistance offered by the outside convective heat transfer. Okay. So basically we have the 4 resistances in series. Okay. So you can easily find out what is the R total, because R total is nothing but summation of inside convective resistance, resistance or conductive resistance offered by the tube wall, conductive resistance offered by the insulation, and convective resistance offered by the outside surrounding air. Okay. So you can find out R total, and from R total you can find out U naught. Once you know U naught, you can find out Q. Okay. So again you can see what is the advantage of applying resistance network and the concept of thermal resistances. Okay. Sometimes what happens is you can have additional resistances. For example, when a fluid is flowing through a tube, let us say that fluid is not very clean, so it can form a scale inside the tube. Okay. So that means there can be a scale formation here. Okay. So what is the effect of the scale formation? There will be another resistance term here because of the scale formation. Okay. There will be resistance term here because of scale formation here, and if you know what is the resistance offered by the scale, you can find out the new overall heat transfer coefficient, right. So this is what we have seen is multimode heat transfer. Now let us look at very briefly about heat exchangers. A heat exchanger is a device in which heat is transferred from one fluid stream to another across a solid surface. Basically most of the common heat exchangers have two fluid streams, one hot stream and the other cold stream. They come in contact through a solid surface, so there will be heat transfer between the hot stream to the cold stream through the solid surface. This is the typical example of a commonly used what is known as recuperative type of heat exchangers, right. And so as you can see, a typical heat exchanger involves both conduction and convection heat transfers, and there are a wide variety of heat exchangers used in practice. In fact, there are many types of heat exchangers available, and you can classify them in a wide variety of ways. So we will look at the classification and different types of heat exchangers when again we deal with the design of evaporators and condensers. At this point, remember that large number of different types of heat exchangers exist. In most of the cases, the heat exchangers operate in a steady state. So we can apply the concept of thermal resistance and the overall heat transfer coefficients very conveniently. And in general, the temperature of the fluid streams vary along the length of the heat exchanger. In the example of multimode heat transfer for a composite cylinder, the temperatures remain constant. That means outside temperature T naught and inside temperature Ti remain constant. So you have a very simple expression, Q is equal to UA into delta T. But in a typical heat exchanger, as the fluids flow through the heat exchangers, their temperature varies along the length. Okay, so you don't have a fixed temperature. So to take care of this temperature variation along length, a mean temperature is defined. This is known as log mean temperature difference, or LMTD. So we have LMTD is introduced and is very widely used in heat exchanger design. So this LMTD is defined as LMTD is equal to delta T1 minus delta T2 divided by ln delta T1 by delta T2, where delta T1 and delta T2 are the temperature differences between the hot and cold streams at the inlet and outlet respectively. So one can be inlet, then 2 will be outlet, or vice versa. Okay, so they are basically the terminal temperature differences between the two fluid streams. So, if you are using LMTD, then the heat transfer rate is simply given by Q is equal to UA into LMTD, and this UA you can write with reference to the outside area, that means you can write it as U naught A naught, or you can also write with reference to inner area, that means UI AI. So, this is a typical expression for heat transfer in a heat exchanger, and this expression given here, that is QA is equal to Q is equal to UA into LMTD, is applicable for pure parallel flow type of heat exchanger and pure counter flow type of heat exchanger. That means when a fluid flows in parallel flow or in counter flow. When they flow in crosswise manner, then it is not applicable. Okay, then we have to add another factor which will consider the other flow directions. Okay, these aspects again we will discuss when we are discussing the design of evaporators and condensers. So, let me quickly summarize what we have learned in this lesson. In the present lesson, we have looked at the basic modes of heat transfer, and we have discussed the basic governing equations, and we have introduced the concepts of thermal resistance and networks to solve steady state multi-mode heat transfer problems, and then we have developed analogies between heat, mass and momentum, and we have also looked at the consequences and usefulness of these analogies. Then we have looked at the basics of heat exchangers. We will be discussing and we will be applying these fundamentals when we do the design of heat exchangers in later chapters. Okay, right, thank you. This lesson are to discuss methods for producing low temperatures, namely sensible cooling by a cold medium, endothermic mixing of substances, phase change processes, expansion of liquids, expansion of gases, thermoelectric methods, and finally magnetic methods. So, at the end of this lesson you should be able to describe various methods of producing low temperatures, perform simple calculations pertaining to these methods, and show relevant processes on TS diagrams. Let us start with an introduction. As you know, in the very first class we have defined refrigeration as the process of cooling of bodies or fluids to temperatures lower than those available in the surroundings at a particular time and place. This is the exact definition of refrigeration. So, here the important thing is to produce refrigeration, it is essential to produce temperatures low enough for heat transfer to take place from the system being refrigerated to the system producing refrigeration. That means, if we want to produce refrigeration in a particular system A, let us say, then we have to take out heat from system A. That means, we have to have another system B whose temperature is lower than system A, so that heat can flow from system A.